Alright, this lesson is about studying the graphs of functions just using the principles of calculus. So the nice thing about this lesson is there's going to be nothing new that's really covered, but it will be more or less an amalgam of the different things that we've learned. So we're going to study the graph of one function by using all of the information about the first derivative and then also the second derivative, and we'll use all of this information to piece together a nice graph of the function. So all I'm really going to do in this lesson is one example in great detail. So we're going to look at the graph of this function, y equals x e to the negative x. Okay, so what I would do in an example like this, pretty much any type of example, is just write down whatever information you think is important about this function, and then what we can do after that is systematically go through and find y prime and find y double prime, and then write down all the information you can about that graph, and then we'll use all that information. So just a couple of random things that we can see about this function. For example, the domain of the graph, this would be x would be valid from negative infinity to positive infinity. So notice you can plug in any number for x here and there will be a y value that's well defined, something that you can calculate. Another random thing, if you can calculate something pretty quickly, you might as well do it. So I can see a point here, a nice one. So a point that's on the graph, if x is 0, then y is also 0. So this is just telling us that the origin, right, is a point that's on the graph. And then maybe one more thing I can see just by looking at this, just by looking at the function, right? You can rewrite it as y equals x over e to the x, right? So you can express e to the negative x this way here. So just one of those random things here. You can see that the bottom function is going to grow much more rapidly in comparison to the top function, and this is the case when x goes to infinity. So as x gets very, very large, you could tell that even though the numerator is going to go to infinity, this is going to get there at a much faster rate. So something that we can write down here, the limit as x gets very, very big of this function, right, just based on this information, this limit is going to be 0. And so that's telling us that this function, as x goes off to the right, is going to get closer and closer to the x-axis because the y values here are shrinking. So the information that we write down here is based entirely on this function, right? You just look for important characteristics, and we just have some random information about the function. So later on in calculus, you can formalize this limit by using L'Hopital's rule, right? Other different results. So this is just kind of an informal observation from that. Okay. After that, what I would do at this point is just go through the first derivative and the second, and then just write down all the information that you can. So I'll do that right now. So here we go, right? So we have y is right here, y equals x e to the negative x. So y prime, we're going to use the product rule here. So this will be the first function and differentiate the second. So notice we have the chain rule here from e to the negative x, and then add the second, e to the negative x, and differentiate the first. Right, so this is what we get for dy dx, and a common factor here is e to the negative x. So I'm going to take that right out and see what's remaining. Okay, so this will give you a 1, and then what we have left here is negative x. So we can write it nice and compact in that form there. So assuming this function is smooth, we're going to set this to 0. And what we're going to do is to pull out the critical numbers, and then that way we can find possible mins and maxes. So an old fact from algebra, right? Something exponential like this, this is never going to equal 0, but it gets asymptotically close to 0. So the only way you're going to have the product of these two equaling 0 is if this term here is equal to 0. So you can see the only value for x where that's true would be x equals 1. So we have x equals 1 here, and this I will label, right? That's our critical number. So that's the special number that we include on the number line. So to finish this off, you can put your little number line here, and this is the sign of the derivative, and so 1 is our partition number, and then you can check on either side of the number 1. So remember, what you're checking here is the actual derivative itself. So I'll repeat y prime, e to the negative x, 1 minus x, and all you care about is checking on the sign. So this expression, right, no matter what you use for x, whether it's positive or negative or 0, this is always going to contribute in a positive way. So it's this term here that's going to influence the sign. So something to the right of 1, like the number 5, we'll get 1 minus 5, and that's going to cause this to be negative. And then something to the left of 1, something like 0, 1 minus 0, and that's going to be positive. So what this is telling us here is our function is increasing to the left of 1, and then decreasing to the right of 1. And so we can visualize this, right, the rise and then the fall. So we're going to have a maximum occurring at 1. So I'll write this information down here. So summarizing here, the function is increasing from negative infinity to 1, right? That's to the left of 1, and then it's dropping, right? Decreasing from 1 onward, so from 1 to infinity. So by the nature of this, we have a relative maximum, right? So we're going to have a maximum at a certain location. That's going to be right at 1. Okay, and then to get the y value here, we have to go into this function. So if you insert 1 in here, we get e to the minus 1. So later on we can talk about approximating that. But this is all the basic information from the first derivative test, right? Using the rise and the fall to classify mins and maxes. So this problem has a high point, but it doesn't have a low point. Alright, so I'm going to repeat this now for y double prime, so that way we can do all of the concavity. And this is y prime here. So I'll get rid of this. And so here we go one more time. So I'm going to borrow this from the earlier work right here. So you'll notice good notation is helpful, right? This is y prime that we're pulling here. And now what we want is y double prime. So I'm going to use the product rule again, using this as the first function and this as the second. So I'm going to write down the first and differentiate the second, so that's a minus 1. And then we'll add to that, writing down the second function, and then differentiate e to the negative x. So this will be e to the negative x, and then the chain rule again, minus 1. So this is y double prime, and we'll use this for concavity. So the factoring here is a bit trickier. E to the negative x with a negative, right, that can be removed outside. So I'm going to do that, and that's going to leave a 1 in this location. So I'm going to pull this right out. So negative e to the negative x, and then we'll see what's remaining. So this will give you just a 1 left, and then for this term it's 1 minus x. So when you simplify this, you get a 2. So this is what I'm seeing for y double prime, for concavity. Negative e to the negative x times 2 minus x. So what we'll do is exactly the same thing, pull out any special numbers here and do the number line analysis, right? So the same type of thing. Okay, so I'm going to get rid of some of this so we have some space. So I'll write this over here. So y double prime, this is equal to negative e to the negative x. And then we have 2 minus x. So what we can do here is, if we set this equal to 0, as we did before, we already noted that the exponential part is not going to equal 0. So the only place where this is going to happen is when the second term is equal to 0, and you can see there x will equal 2. So we have to be careful here, as we've talked about this before. This is not a critical number, not going to lead to a min or a max, but this is a possible point of inflection. So I like to call this PPOI. So we don't know if it's a point of inflection yet because we haven't talked about the concavity on either side, but it's definitely a candidate for an inflection point. Okay, so when we do this kind of thing, we go into the number line here, and we're going to look at the sign of y double prime here. And so our number that's going to break the number line is 2, and we're going to check on either side. So the thing that we're checking here is the second derivative. So we have it here. So I'll repeat it so we can see it. Right, so there's the second derivative. And so notice that this first term here will always contribute in a negative way. So the exponential is a positive number, but we're negating it. So basically this is going to drive the sign of the second derivative. So we'll pick something like the number 7 here, and this will be 2 minus 7. So this will be negative, and the product of these two is positive. So if you remember, the second derivative tells us about concavity, so the graph is concave upward to the right of 2. And so in a similar way, if you try a number like 0, right, to the left of 2, 2 minus 0 is now positive, right? So the product of these two is now negative. So concave downward there. So again, the graph is smooth, so 2 is not just a possible inflection point, it will be a bona fide point of inflection. So we'll write down a couple of things here. We have downward concavity, where we see the negative, so negative infinity to 2, and then we have upward concavity to the right of 2. So far, so good. And then we have an inflection point here, so we can call this a point of inflection. And this is occurring at 2. At 2. And just like we did for mins and maxes, you have to go back into the function and insert x equals 2. So this will be 2e to the negative 2. Probably a pretty small number. And so that looks like the full analysis of y prime and y double prime. So we have all the information about the way the curve bends here, and then we also have an inflection point. So the hard work here is done. I'm going to wrap this up just by summarizing the information that we found, and then what we'll do is to try to freehand a graph. So this has all of the information that I just did in detail here in this lesson. So we have the increasing, decreasing information, a high point at 1, comma 1 over e, and this is the estimator here, and then the concavity information, the inflection point with an estimate, and then also the earlier remark where as x approaches infinity, the graph is going to tend to 0. So I'm going to try to do a decent graph here. We'll see what I can do. And I'm trying to think about the different numbers that we see up here. They're pretty small. The important information is really occurring at 1 and 2. So I'm going to put 1 here, 2 here, possibly 3. So I'm going to scale these exactly as they appear. But then if you look at the y-coordinates, they are quite small, 0.37, 0.27. So I'm going to call this 1/2 up here. So you'll notice if you graph this on a standard window, you might end up not seeing that much. So you really want to pick a scale that's suitable or related to the information that you're finding. So I'll write down the function here again, just so we can see it. So all of the analysis took place with this function. And so some of the earlier comments I made, the first one was that the origin, right, is a point that is directly on the graph. And then after that, I think we can just plot some of the information. So I would go after the extreme values and the inflection point. So there's a max at 1.37. So I'll try to find that. That's around 0.4 so on the y. So I'm going to put a dot right there. And then there's an inflection point at 0.27. So it's about halfway up to 0.5. So I'm just judging this by eye. So those are the 2 points that we found. And then the information here is it's increasing to the left of 1 and decreasing to the right of 1. So that seems to make sense with what we're seeing in the graph. And so I'm going to piece together this information here. So we seem to have this kind of thing that's going on there. And notice it is concave downward all the way to this point, to the left of 2. So I'm going to continue the downward concavity here. So this is the way that the graph looks. So we should agree that to the left of 2 the graph appears concave downward, but then as soon as you hit 2, the concavity changes. And that's where this information on 5 becomes important. So because the concavity is going to flip, now it makes sense that this limit is going to be 0. So we're going to show upward concavity here, and then the graph becomes asymptotic to the x-axis. So if you were to look over here for large x, this branch of the function gets closer and closer to the x-axis. So you can see all of the information that we get here comes from the calculus, right? And you can see your maximum right here, maximum value, and then right over here we can see our inflection point, right? The point of inflection. And so that's how you do a full analysis of a graph. All of the information that we have collected here comes directly from looking at dy dx here, and then also the second derivative, and then we collect all of this information and then import it right into a graph.